Hi everyone, our weekly CnosDB live streaming is back. In this episode, we'll be discussing the topic of stream processing again. Without further ado, let's dive into the main topic. If you haven't watched the previous lesson, you may find this section a bit confusing. I think you can catch up later when you have time. If you are interested, you can review the content from the previous lesson. Next, we'll discuss the core component of structured stream, some of the essential components and the core ones. Let's start by defining data sources for stream processing. You can say there are several types, including source, microbatch streaming, and continuous stream. The first one has two versions, version 1 and version 2, but we won't go into details here. Now, let's look at the microbatch stream, which is designed for the version 2 interface. This interface involves three critical methods. One is to get the latest offset of the data source. This offset is essential for reading data. The second is the input partition, which can be thought of as a data partitions. It's like saying my data source can have multiple partitions. You need to specify the starting and ending offsets and return multiple data partitions. The partition reader factory is responsible for getting a partition reader for a specific partition based on the input partition obtained in the second method. The following content is related to continuous stream because structured streaming has two modes, VP mode and the lowering mode. Now, let's talk about the lowering mode first. This mode requires a specific data source because it's still experimental and not widely used. So we won't dive into the details here, and we haven't referenced it yet. After discussing data sources, let's move on to the next topic. Once we have our data source, the next step is to process it. So we need a trigger. This trigger essentially determines how we incrementally activate the processing logic for this data. There are several types of triggers, and let's take a look. First, we have the default mode. In this default mode, once the previous batch processing is completed, the next batch processing starts immediately without any waiting time. It's a continuous, non-stop execution. Next, we have the processing time trigger. This can be thought of as triggering VP processing at regular intervals. How to understand this? It has a few scenarios. For instance, if a time interval has passed, or if it triggers every 2 seconds, when the previous VP processing was completed within 2 seconds, the next one begins immediately. If the previous processing took longer than 2 seconds, say more than the defined time interval, then the next VP processing starts as soon as the previous one finishes. But if during the current batch's processing, there's no data arriving, then there's no need to execute VP processing for that batch. And there's one more type, which is the one-time trigger. As the name suggested, it's executed just once. In other words, it retrieves all the data from the data source, then it processes the data all at once. Essentially, this is more like a batch processing. There's another type called available now trigger. This is actually similar to the one-time trigger. It also processes your data source all at once. However, there's a difference. It means I may process your data source in multiple classes, increasing parallelism by splitting your data source into multiple pieces. For example, if your data source is a file, you can configure how many files to read each time you trigger. This means I might translate your data multiple times to process it entirely. But once processing is done, the task ends. Unlike the default of processing time trigger mode, which are persistent tasks. Now, let's move on to continuous trigger. Continuous trigger is used within the available now trigger mode, but we won't go into the details here. After covering this point, let's continue. Trigger represent what we need to do before processing the BP data for this data. VP data, well, what preparations do we need to make before processing it? We need to write WAL. As you already know, if we want to build a highly available system, we definitely need WAL. What's it for? It's for disaster recovery. In case our program crashes or there are machine failures. When we pick up the streaming task again, we can continue from where we left off, thanks to the information stored in the WAL. So, what does WAL specifically do? It mainly records the offset corresponding to your data source and accumulates other data. For example, where is the offset currently? And it stores this in the HDFS under a checkpoints directory, which you can configure. Within the checkpoints directory, there's an offset subdirectory, and each VP processing has a corresponding batch ID. WAL records record a file for each VP processing, and the file name is the batch ID. As for the file's content, it's a serialized structure represented in the blue box on the left, which can be considered similar to a JSON format, and is written to the file. Inside the structure, there are two main components: the offset, which corresponds to the data source offset in order, and offset metadata, which includes the original data, current watermark, and the timestamp of the current VP processing. There's also some configuration information attached. On the right-hand side is the content serialized within the environment. Of course, the offset is abstract because different data sources may have different offset implementations. So this is what we write before each VP processing, is to record the information needed in case of failures. Well, now, if during VP processing something goes wrong, we have a state store. The state store mainly records some stateful operations, such as aggregations and other stateful operations. Why do we call them stateful? As we mentioned in the previous session, for aggregations, if we are aggregating data in buckets over time, it's not guaranteed that all data within a bucket will be processed in one VP processing. So we need a state store to save the state and use it for a subsequent VP processing. The state store needs to have version numbers because we also need to do fault tolerance. When we are doing fault tolerance, we only need to record two version numbers. One dictating that we have completed processing, another indicating the one currently being processed. State store data is stored in a key value format. The key is, for example, the group by key for aggregations. Currently, there are two implementations of the state store. One is HDFS, using earlier versions for performance reasons. But starting from version 3.2, RockDB is used for better performance. If you don't want to use either of this, you can also extend the state store provider interface. So, after discussing the state store, let's move on to the VP processing that takes place after these steps. So, what should we do next? After I have completed processing, I definitely need to log that I finished processing. Otherwise, when a fault occurs, I won't know if your request was executed or not during the fault. If it wasn't, I'll need to reprocess it. If it was executed, then I don't need to execute it again. This commit log is actually placed in a checkpoint directory that you have configured. The specific contents of the commit log are quite simple. For each VP processing, it creates a commit log file, and the file name is based on the batch ID, which is similar to the WL-ID. So, what's in the commit log? It's straightforward. The commit log contains the watermark that will be used in the next VP processing. What is a watermark, and what is its purpose? We discussed this in the previous session. If you are not familiar with it, you can review the previous content. As for when this commit log is written, it happens right after triggering the VP request, recording the offset into the WL, and initiate the actual VP processing. After processing, the commit log is written, and then we process with the next VP processing. After that, we can look at the data output. Each time we complete a VP request, we need to output the data. We discussed output mode in the previous content. There are several output modes: complete mode, append mode, and update mode. Complete mode means that I output all historical data each time I process a request and save the result of the current VP processing in the state store. This means that the state store's data volumes keeps growing without a cleanup mechanism, so it's rarely used. Append mode does exactly what it sounds like. It appends the data to the output without any updates, ensuring that I don't produce duplicate records of the same data. The third mode is update mode. In this mode, it outputs data every time it completes a VP processing request. This mode is useful when you want to update data for certain scenarios. For example, if you are aggregating data by time buckets and you have processed part of the data during one VP processing, you may want to output the current maximum value. Then, during the next VP processing, when more data arrives for the same time bucket, the maximum value may change. And if you output the updated value, in this scenario, the sink must support an update mode, as discussed in structured streaming. The sink you use should be idempotent, meaning it allows you to override the same data. Now, these three output modes in practice, append mode and update mode, are more commonly used. Complete mode is less frequent due to the significant memory overhead it occurs. These capabilities also depend on the specific use cases and requirements. Next, let's discuss some other important components that are involved in stream processing. First, let's talk about watermark. Watermark is a fundamental concept in stream processing because it serves two main purposes. First, it helps in handling delayed data, and second, it aids in cleaning up historical data from the state store. As far as calculating watermarks, I've looked into two methods, structured streaming and Apache Flink. In structured streaming, it's relatively simple. Watermark is calculated based on the maximum inventory in the data from the previous VP processing, minus the maximum allowed delay you have configured. This value represents the watermark for the next VP processor. On the other hand, Apache Flink offers more flexibility. Watermark calculation strategies can be customized. Flink provides several built-in strategies, such as the ingesting time, which only allows the watermark to advance, and user-defined strategies where you can define how to calculate the watermark based on your application's requirements. This watermark calculation is crucial to ensuring time-based operations in stream processing. We can see that event time is crucial in stream processing. Event time needs to be tracked or recorded after each repeat processing is completed. There will be a watermark trapper responsible for keeping track of and updating the watermark. In structured streaming, there's a strategy for watermark. One, because, for example, we are dealing with a union operation that involves multiple tables. Each table may have different watermark settings. Structured streaming computes a global watermark by considering all these watermarks. There are different strategies, such as taking the maximum or minimum among all the watermarks. Earlier, we talked about state storage. We also touched on the concept of stateful operators. Because there are various stateful operators like aggregation, deduplication, join, and more. Among them, aggregation is the most commonly used, especially in time series databases, where it covers most use cases. In this context, I'll only discuss aggregation. The aggregation operation is crucial. I will dive into how to enhance this important aspect by introducing the concept of state storage. As we mentioned earlier in Sparks, RocksDB is used to store this state. Let's talk about the parameters for the state. We'll discuss what parameters needed to be recorded, and what behaviors need to be implemented when creating a state parameter. We have listed some important state parameters here. One is query ID, which, for example, is necessary to uniquely identify cycles. Every cycle should have a unique query ID. This is important for scenarios where we need to locate a specific cycle after a system failure or restart. Next, we have a run ID. This value changes when a machine starts or when it restarts, and it essentially represents the life cycle of the application from start to finish or from start to an expected failure. Batch ID is related to each repeat processing task in the stream processing job. It identifies a specific batch of data. Additionally, since parallel computing requires data partitioning, there is information related to partition IDs. These are just some of the important parameters, as there is a wealth of information involved. Now, the state storage needs to support source committing and source interruption. We are processing data streams continuously and line by line. You can only commit the source transaction once all the data related to the current VP processing has been processed. This ensures data consistency. Without this, you might have partially written and processed data, leading to inconsistency. This imposes certain requirements on handling the data. Now, let's discuss stream processing. Stream processing in Rust has been extended to include functionalities related to stream engine and introduces some stream-related operators. In the upcoming sections, we will talk about these added operators and explain how they transition from logic plans to feeder plans. First, let's look at the event time watermark logic operator. Its primary purpose is to update the original data within this batch of data. It essentially tags this batch with information about the event time column. This tagging helps downstream operators understand which column contains event time data, making it easier to process. For example, it's crucial in the early stage of the state storage and aggregation, since they need to work with this event time information. Another important use case is tracking the maximum event time within the data batch. We touch on the watermark tracker, which is responsible for tracking the maximum event time within the data batch. This is crucial for calculating the event time needed for the next round of processing. The event time watermark logic operator includes several properties, such as the event time column, watermark, and the maximum power-rated delay, which will be explained later. Let's move on to how we can transition from a logic plan to a feeder plan. In structured streaming, we have expanded the functionality of stream processing and introduced as a series of transformation rules. First, I'll mention the stateful aggregation strategy. It's primarily used for transforming aggregation operations. Then there's a flat map group with state strategy and streaming duplication for handling the global lineup. For now, we'll focus on the aggregation operation. So, how does the aggregation operator transition from a logic mode to a physical mode? This process involves two key operators: event time on watermark and aggregation. Event time watermark can be easily converted from a logical to physical. The attributes of these two are quite similar. Aggregation nodes present two scenarios, one with session windows and one without. I'll describe the case without session windows. For example, if we encounter an aggregation logic mode, it gets transformed into an addition aggregation. This represents a local or partial aggregation. Then we add a shuffle mode, equivalent to an exchange mode in Spark. Following that, we perform a partial merge aggregation, which involves merging locally aggregated data. Subsequently, we add a state store restore execution, which relates to a state storage, as we will discuss later. Then we include another partial merge step for local merging. And finally, we do a state stored save operation, which is also related to state storage. This entire sequence leads to a final aggregation operation. So, in a nutshell, a logical aggregation node goes through multiple transformations to become a physical plan. Here's a visual representation of the execution plan. starting with a table scan and then adding a event time watermark mode. We proceed to aggregate the data. First, with a partial add, then a shuffle, followed by a partial merge aggregation. And finally, a state store restore execution. The process continues with another partial merge and concludes with a state store save. All of this leads to a final aggregation. The state store restore execution takes care of preserving the historical data of VP request output as an immediate state in the state storage. This operation is necessary to combine the current logical aggregation result with historical data for each rule. Following this, another partial merge takes place, consolidating the data. Lastly, we do a state store save to store the current immediate state for future BP processing, ensuring continuity. Once the saving is done, we perform our final aggregation to complete the process. It's important to know that we have various output modes, including full output, append, and update. We'll dive into the logic behind this mode later. In essence, this is the flow of aggregation within this extended physical plan. So let's proceed with this stream processing extension. Now, let's discuss the time watermark operator. To be honest, there's not much to say about it. Its properties are similar to the logical operators we discussed earlier. Next up is the state store restore operator. We mentioned this briefly when we were looking at the diagram. What's special about this operator is that it retrieves data from the state store based on the group by key. In other words, it fetches data from the state storage relevant to the data involved in batch processing. After retrieving this data, it combines records with the same key. The key thing to note is that it usually occurs after partition merge operator. Its output and input schema remains unchanged. It doesn't alter the data types. Its operation is relatively straightforward. It's all about retrieving data from state storage and removing expired or outdated information. Now, let's talk about state store save operator. This operator is quite significant, especially in the context of aggregation operations. It's essential because, in my opinion, this operator plays a vital role in aggregation operations. Let's explore what it does. It operates on individual records, and for each record, it calculates a K based on that grouping attribute. This K is then linked to the state store. The input and output data characteristics remain consistent without any changes. Importantly, it's the output mode that distinguishes its behavior. First, let's examine the full output mode. In this mode, all data is written to the state store after it's received from the upstream source. Then, after saving this batch of data, it's all retrieved from the state store and sent downstream. The key here is that it saves the current batch of data and also retrieves all the data from the state store, which includes historical data. Next is the append output mode. It's slightly different from the full output mode because, in this case, it saves the data that's overdue based on the watermark. This mode necessitates configuring the output, the watermark. When the operator receives data from upstream, it only retains data later than the watermark. Anything earlier is considered outdated and isn't saved. After seeing this data, it proceeds to remove all outdated information from the state store and then output the remaining data. Finally, we have the update output mode. In this mode, like the append output mode, it retains only the data later than the watermark. This data is saved to the state store and is subsequently output to the downstream source. However, there's a difference. In the update output mode, data is only output once, whereas the append output mode, the same data might be output multiple times. The crucial distinction lies in the behavior of when data is sent downstream. The update output mode only sends data once it's outdated, while the append output mode sends data as soon as it's saved. I know it can be a little bit confusing, but essentially, the update output mode only output data once it is outdated, which means it could be from the same window or batch of data, but processed at different times. The append output mode, on the other hand, output data as soon as it's saved, regardless of its outdated status. It might be easier to grasp if you have gone through the use cases and examples in the previous sessions. Now you will find a specific execution plan, which is quite similar to the diagram we discussed earlier. I won't go into the details here now. The session window operators and the session value state operators, as well as the session window store, are extensions for handling more complex scenarios in stream processing. We might plan to implement session window in the future, but we will dive into that when the time comes. Lastly, once the execution plan is constructed, we add various operators to it. We have covered a lot of today, and we hope you have been able to follow along. If you have any questions or need further clarifications, feel free to reach out. We are here to help. We have added some transformation rules to the plan. Specifically, in stream processing, there are various constraints that need to be addressed. To ensure that generated plans are correct, we have a checker that verifies these plans. There are numerous constraints involved, but we won't go into specific details here. In this session, we have covered a lot of ground. We'll mainly focus on extending logic nodes, physical nodes, and optimization rules in the batch processing C code engine to accommodate stream processing. Keep in mind that what I covered today might be just a portion of the overall picture. There are many details and other aspects we haven't discussed because our focus is on the client series database. That wraps up this session. Thank you, and I hope you are looking forward to the next one. Oh, by the way, CnosDB Cloud is live now, and you can join our free trial at this link right here. Join our Discord group here as well. Thank you. Bye-bye. See you in the cloud.